Welcome to your Unit 5 pre-lecture on collision theory. I will have previously introduced, um, let's see, I would have previously introduced average reaction rate. We're looking at kinetics and how we explain the rate of reactions at the particulate level for reaction completion. And collision theory is going to sound very similar to another theory that we talked about with gases, known as kinetic molecular theory, right? So what we say, though, this is a kind of more general theory that isn't just assigned to gas particles, but now we're looking at overall what's happening between particles in any reaction, despite the state of matter it's in. And we're saying reactions must occur through particle collision and depend on two things according to collision theory. One, the number of collision, so i.e. the frequency of collision. And two, the percent or fraction of particles that collide with enough energy, okay, known as what we call activation energy, to successfully break old bonds and complete formation of new bonds. By the way, if you think back to our unit 2 topic or unit 3 topic of Maxwell-Boltzmann distribution curve, on the curve, that was where you saw the shaded part on the curve of percent of particles that could actually complete a reaction. This is what it's referring to, is the Maxwell-Boltzmann curve is a visual of us being identified. Well, out of all the particles colliding, what's the percentage of them that's actually going to lead to my reaction? And that's going to help me understand my rate of reaction as well. Okay, so from these two postulates or principles of collision theory, we get a couple of things that we analyze when studying and understanding the kinetics of a reaction. One of them is that in order to have effective collision, okay, and this is actually one of the main ones, in order to have effective collision, you must, okay, you must have particles collide with an energy amount, particularly a kinetic energy, with a energy, okay, equivalent or greater or equal or greater to the necessary activation energy. And activation energy is defined as the minimum amount of kinetic energy oh boy, kinetic, oh man, this is not writing very well. Energy, okay, required, hold on, required to have a reaction occur, to initiate or activate reaction. Okay. So why are there so many ants on my desk? I'm dying over here. Ah, okay. Sorry, we're just having ant infestation. Okay. Activation energy is symbolized as E subscript A. And what we say it is that when looking at a quantitative perspective that we will eventually graph later in class, it is the difference between the energy of breaking and forming. All right. The bonds. And just so you know, breaking bonds always requires energy and forming always releases energy. So it's the difference between these two energy values. Okay. So this is probably the number one factor in manipulating and understanding the rate of a reaction. And so that begs the question, well, can we change this activation energy? If this is kind of like the gatekeeper of reaction completion. And here we see our Maxwell-Boltzmann showing us, that it is possible. If we look at particularly temperature, there are some factors that coincide with previously discussed factors that affect reaction rate that we can shift the particles or shift the curve over to have a greater amount of particles that are able to achieve the necessary activation energy. But there's also another way we can do it, which is through a catalyst. Okay. And so when we think about this, is temperature itself doesn't actually change the activation energy. It just changes the particles percent that can reach the activation energy. So temperature only changes the percent of particles that can reach activation energy. But to change the activation energy value, to actually change that value, that can, okay? But to actually change the activation energy value, only one method exists. And that is the use or the addition of a catalyst. Okay, the addition of a catalyst. And here's why. The activation energy is inherently connected to the mechanism or the exact way that the particles collide. We could call it the pathway of particle collision. And so it's like looking at a race and saying, I'm actually changing the course that you're running. I'm not just making the racers faster. So temperature is like giving a racer like an adrenaline boost that makes him run faster, but not changing the course itself. He still has to cover the like 13.1 miles of a half marathon. But a catalyst is like changing the actual pathway of the marathon so that the same what is that called? Unactivated, or the same caffeinated runner could still achieve at a faster rate the marathon because you simply shortened it, right? So that's kind of like the idea of why a catalyst source is. It actually changes the pathway. It changes the pathway for particle collision. Okay, whereas temperature just makes the particles better. Here, temperature simply only affects particles, not the pathway. Okay, so there's one more factor to also consider, and that is the positioning of the particles. And this ties directly in with the idea of particle pathway or mechanism, is that the way the particles collide also impact the effectiveness or the successfulness of a reaction completion. So the particles must collide, one, frequently, but two, in the proper orientation, okay, to produce desired results. Okay, so if we look here, we have two examples of the same reactants, CO, carbon monoxide, and nitrogen dioxide. But here we have the collision occurring with oxygen forward, and here we have the collision occurring with nitrogen forward. And what we get is in this collision, we actually get no successful reaction occurring, or sometimes we get byproducts, which are undesired products due to the different collisions. And then in the first one, we actually get a transformation of the molecules, the breaking and forming of new ones to CO2 and nitrogen monoxide, okay? So as a quick summary of the factors that increase collision, we can refer back to that which was previously discussed, this is the previous methods of increasing rate of reaction and therefore collision, which was increasing surface area, right? Increasing ants everywhere, increasing surface area, increasing amount, increasing temperature, which is a favorable one, increasing pressure for gases. Okay. And then if we talk about the current methods that are introduced via understanding collision theory, or the newer, maybe I should say not newer, I should say newer. Okay. We can add a catalyst to change the activation energy. And we can also help ensure proper orientation or positioning of the particles during collision. Notice something, the previous factors kind of emphasize part one of collision theory, the number of collisions. It addresses the particles, frequency or collision. And this one tends to address pathway of collision or mechanism. Okay, so that's your summary on collision theory. And tomorrow we'll talk about how we quantify and express in a mathematical expression, rate law and rate of a reaction, and the individual role that each reactant species plays in it. All right, guys, good luck.